Okay, welcome to our very first lesson in Algebra 3 and Trigonometry. We're going to start off today with a very basic lesson, or I feel it's a very basic lesson, hoping to make sure we're all on the same page with a couple little things as we move forward. So this is lesson 1 from our chapter 1, dealing with graphs of equations. And we're going to be testing symmetry, and we're going to be looking at basic equations of circles for the most part. That's our two bigger things here. So you might hear this statement every once in a while saying, here's an equation in two variables, or write an equation in two variables. And for some reason, this just gets a little confusing, but it's really just the equations that we're familiar with. Like this. This is a linear equation, and this equation is in two variables, right? There's a y variable and an x variable. Now we should know this is a linear equation. Not only that, we know it's in slope-intercept form. Or likewise, we have this. This is also in two variables. It's only got a y and an x. That's my two variables in here. We know that this one is a quadratic. And yeah, so it's got two variables in it. That's really all that matters. But most of what we do in algebra is based off equations with two variables. And it's usually an x and a y, especially when we're dealing with graphs of these equations, which we are going to be doing today. And what I want you to understand is we have these coordinates. We have these things called x, comma, y, or 1, comma, 3, or whatever you want to call it, a, comma, b. And yes, they're coordinates. Yes, they're points on a graph. But what we want to understand is that also we could call these solutions to an equation that makes the statement true, or makes the equation. Remember, an equation is just a statement. And whenever I say statement, it's usually whatever is being written right there. This quadratic here is a statement. Okay, so a solution to these equations is some coordinate that makes the statement true. So in this case, in the linear case, if I plugged in x equals 1, I get out the answer 1. So 1, 1 is a solution to this equation. Or the solution 2, comma, 4. That's also part of my equation. It's a solution to my equation. So I'm really stressing this word solution. And we should understand that a graph is the set of all solution points to an equation. Most of us have just thought of linear equations, that's 3x minus 2, so it looks a little bit something like this, as just a line. But some people forget that it's not really a line, it's just a whole bunch of points. And it's a set of infinitely many points. They're really, really close together. And all of these points on this line are solutions to this equation. So the point 1, 1 is like right in here somewhere. The point 2, 4 is right up here somewhere. And those are all solutions to our equation. All right, so that's just a couple basic definitions. Moving forward here, another something we should really, really understand, because these are kind of real-world coordinates that get used quite often when we're looking at real-world problems. First of them is our x-intercepts, and you just need to know that in order to find an x-intercept, you substitute y equals 0 and solve for x. So if we just started with our y equals 3x minus 2, I would set y equal to 0, and then I would solve for x. So I would add 2, and I would divide by 3. And this would tell me that the coordinate 2/3, comma, 0 is our x-intercept, or it's the solution that crosses the x-axis, or it's at the x-axis. And likewise for our y-intercepts is when we substitute x equals 0. So if we did that for the same equation, we got 3x minus 2. We want to find when x is 0. And I know you learned this in Algebra 1 somewhere along the line, but we just need to refresh our memories because it gets lost in the cobweb somewhere. Okay, so 3 times 0 is 0, minus 2 is negative 2. So the coordinate, make sure when you're telling me what the x-intercept is, write it as a coordinate. What the y-intercept is, it's a coordinate. It's a solution point. 0, comma, negative 2. Remember, x was 0, y was negative 2 in this case. All right, moving right along, we have symmetry. This always kind of throws people for the loop because of the way it's defined. If we're talking about symmetry with respect to the x-axis, that would be something along this line. Something that is exactly the same above as it is below the x-axis. Now, some of you might remember that this is a non-function. We'll get to that later in this chapter, but this is a non-function because it fails vertical line tests and all that sort of stuff. But we can have equations that represent this line, and we could talk about it as being symmetric about the x-axis. And here's what usually throws people: the definition. If x comma y is on the graph, so is x negative y. And what we're basically doing is if we substitute in a negative y and we get the same exact equation. And I think I have this on the next slide, but I'm going to kind of jump the gun here. Let's say this equation was x equals y squared plus 3. All right? And I think it actually is. I think this is actually y squared plus 3. If I was to plug in a negative y value just to see what would happen, I would take that negative y and I would square it. Well, negative squared is just positive. And because those two things are the same, that tells me the equation, without even looking at the graph, that this equation, when graphed, would be symmetric about the x-axis. So we want to substitute in the negative y. Likewise, with respect to the y-axis, would look something like a normal quadratic, a straight up and down quadratic, symmetric on the x-axis, where this one could be y equals x squared plus 3. And in order to be symmetric about the y-axis, if the point x comma y, so I didn't put this on the last graph, but if this point here is x comma y, the point on the opposite side is negative x comma y, same y value. And likewise, we would substitute negative x. We would say y equals negative x squared plus 3, plus 3. And we say y equals x squared plus 3. We notice that they are the same thing. And lastly, there's one more type of symmetry. The x and the y axes, the symmetry about those two, they are line symmetry, which means you can fold it across that line and it'll be the same. Whereas we have a third one, which is respect to the origin, which is not line symmetry, but it's actually rotational symmetry. And that would be something like this, where if you looked at that point, let's say it goes through the point 0, 0, if the point x comma y is on the graph, so is the point opposite of x, opposite of y on the graph. And some of you might remember that this is the function y equals x cubed. So if we plugged in negative x and negative y, so I want to plug in negative y and negative x. Well, negative y doesn't do anything. If I cube a negative number, it remains negative. But now I can divide both sides by negative 1, and I would get y equals x cubed. And because this equation is exactly the same as the original equation, this tells me that it is symmetric about the origin. And now, in order to figure out what that really kind of means graphically is if you rotated 180 degrees your graph or flipped it upside down sort of thing, it would look exactly the same as if when you started. So you can rotate this one all the way around and it will look exactly the same. You can actually lift up if you're watching on your phone, you can lift or you rotate your phone and you'll notice that this one is exactly the same upside down or right side up. All right, so that's the basic way, and this is what I told you I was jumping the gun anyway. So you can say, so you can write this down. So for testing symmetry, this is what I did. For the x-axis, I replaced the y value with a negative y. Notice I used variables. You cannot just plug in numbers either. If I plugged in a negative y and it yields an equivalent equation, or as I mentioned, if the equation is exactly the same as when it started, then you're good. And then same goes for the y-axis. You replace x with your negative x, and it comes out with an equivalent equation. And lastly here, if you were to plug in negative x and negative y, and it comes out with the same equation. Now notice I'm talking about if it actually does. If any of these statements come out to be false, then it's not symmetric. So if I plugged in a negative y and it doesn't come out to an equivalent equation, then it's not symmetric about the x-axis. Likewise, if I do this for the y and it doesn't come out, then it's not symmetric about the y-axis. Not all functions or not all graphs have symmetry, and actually more functions, I could kind of say this, you'll more often see functions or equations that don't have symmetry or these types of symmetry than you will with these types of symmetry. All right, let's go ahead and move forward. Last thing we're going to look at here is the equation of a circle. Again, some of you might remember this from geometry. I don't think this is in Algebra 1, but you might see it from geometry and from Algebra 2. These are very handy equations. We're going to elaborate on these equations a little bit later when we get into our conic sections chapter. But right now we just want to know the standard form equation, and it's based off of having some center of your circle at h comma k with some radius of r. So if you had yourself a graph, and here is the center, which is h comma k, and let's see how well I can draw a circle on here. It's not the worst one I've ever drawn. Okay, and then you have some sort of radius. You can determine the equation of a circle just from this very, very simple statement. So it's x minus h quantity squared. When I say quantity, that means the entire thing gets squared, plus y minus k squared, quantity squared, equals the radius squared. And if you were to really think about it, and if the center was at 0, 0, that means h is 0 and k is 0. It'd be a much simpler equation where it's x squared plus y squared equals r squared. And that might even look a little bit familiar because that's kind of our Pythagorean theorem. Leg squared plus leg squared is hypotenuse squared. We'll get to that a little bit later. It's also our distance formula. You notice this is the distance between two x values squared plus the distance between two y values squared is equal to the hypotenuse squared. All right, this is kind of interesting how circles and triangles are somehow connected by the way we define the equation of a circle. And now I know that might be over the head of quite a few of you, but I just want you to try to think about that. By thinking about the math, you get actually a little bit better at the math. So if I was to give you an equation like this, we hope to be able to pick out what is the center and what is the radius. And here's how I usually just help people out when they don't understand this HK thing. The center is basically what makes this piece 0. Well, if I plug in an x equals 3, 3 minus 3 is 0, which means the positive 3 is my x coordinate of my center. And if I plug in a positive 4 here, that makes this 0. Therefore, 4 is the y coordinate to my center. And since the radius is squared in my equation, 25 is not my radius. My radius is going to be whatever squared gets 25, and we know that to be 5. And therefore, we could have a center of 3, 4 with a radius of 5. And our last one here is, let me erase some of this stuff off the page. Same idea. What makes the first piece 0? Well, that's going to be, here's our center. Our center is going to be, what makes the first thing 0? Well, I know -9 is going to make that a 0. And what makes the second thing 0? Well, there's nothing there, so it's going to be a 0. So the center to my circle is -9, 0. And my radius is going to be, you might realize this, that the square root of 25 was 5. So we need to find what is the square root of 32. Well, just for those of you guys that can't remember how to do this, 32 is actually 16 times 2. And the square root of 16 is 4. And a radical 2. And that's where I want you to leave it. Do not give me a decimal answer unless it asks for it. So there we go. We have the center of -9, 0 and a radius of 4 root 2. So I hope you learned something. And if it wasn't anything new, I hope it reinforced some of those skills that you may have forgotten. Here's your assignment. I will try to have an assignment sheet for the entire chapter ready for you on Monday. But what I want you guys to do after this video is I want you to sit down. I want you to try some of these problems, see how they feel. We will be working on this in class. This is actually the plan for class, is that we work on this, what is this, 13, probably 20 problems. All right, I hope you guys learned something, and have a good evening, and I will see you guys tomorrow.